teach in biology and museum studies. I'm going to be getting a great chance to meet with you guys on Wednesday, October 15th. Ahead of time here, I'm doing a reading guide to guide you through the few pages that you're going to read in the textbook. A lot of ecology is really complicated and a bit messy, which you might have discovered with your recent field projects. Population biology, however, is much less so. You can use a very simple table with data about birth and death in a population, and you can gain really important insights into how a population changes over time. With a little practice, you will be able to make your own life tables and use them to predict population trends over time. This chapter here gives you a really good introduction to that. I'm going to point out a few sections and pose some questions to you. The way that I do reading guides is I say these questions, I want you to write them down, and then answer them for yourself while you're reading, and that will help guide you to focus on the important points. This section here called Life Tables can be based on blah blah blah. This section should really read, what is a life table and how can they vary? This is your introduction to life tables, and they've got an example life table here for you. When you're reading this, I want you to think about which of these columns, right, here's one column, 2, 3, survivorship, fecundity, which of these columns come from data that you measure for the population in the field? Which of these columns are calculated then from other information that you collected, right? So which is coming from raw data and which is a calculation based off of that data? I want to point out a little bit about notation, right? You have an X here, and this tells you that things in this column are called X, right? And they relate to the age of the organism. But you also see this little X here next to N and next to S and next to L and next to the F here. That little X after each term, that means that it's with respect to X, right? So this big N means the number alive with respect to this X, which means the number alive of this age X, right? So there are 843 individuals of age 0, that is not yet turned 1, or in this case, not yet turned 3 months, okay? So this S of X then means that this is the survival rate here for individuals that are in this 0 age class, okay? So that's what that X means. It's just telling you what that number is calculated based on, okay? In this section, they will tell you about 2 different types of life tables. I want you to know what those tables are, okay? Cohort and static. Know what those are, and for what types of populations would you prefer one versus the other? And these are questions that I will ask you during the lecture, so please make sure that you answer these. Okay, now for static life tables here, what is it that you need to know about each individual, or that you need to be able to estimate to be able to use a static life table rather than a cohort life table? And then for the static life table, what assumption do you need to make, and specifically to calculate survival rates if you're using a static life table? When is that assumption likely to be valid or invalid? Think about environmental conditions. Okay, I want to point out, so I said that this section should be titled, what is a life table and how does it vary? So getting back to that, in particular, how does this first column vary? Right here we have some measure of age, right? We have a measure of age in 3-month spans. What else can this be a measurement of? It relates to age, but what else? So look through the text and find that. Okay, we're going to go on to the next page here. Here, this next section on life table data for people, section here. Now we're getting into something where there's another table, okay? I've already pointed out this previous table and asked you to think about what each column means. In general, when you find a table or a figure in your textbook or in a paper, it's there because it's very important. Many times when you're reading a scientific article, if you can understand only the tables, you will be perfect. You will understand basically the whole paper. So always pay attention to these tables. In this, if we use the values we calculate in the life table, we can actually plot those values on a graph. So a table is a good way of organizing data, but it's not always the best way to interpret the data or to show the data to make it interpretable. So here we have in figure 10.4 down here, we have the survivorship plotted here, okay? So x-axis is age, right? So that's basically this first column, right? X. We also have survivorship is a percent, right? So here you have survivorship, but this is not a percent, right? So if you take this number and multiply it by 100, that's how you get the number here and how you plotted it here. Okay, so figure 10.4, if you look at this graph for a while, this shows a startling effect of human infant environmental conditions on the rest of their life, particularly for Gambians. This is an incredible effect. I want you to take a moment to answer the question that is posed in the legend over here. So as you're reading through that, make sure you can answer this question. Okay, now the shape of these curves here, where they've plotted survivorship, right, over age, these can be generalized, and so as we go further, they're going to start to generalize these curves, right? You have this curve that arcs like this, and you have this curve that goes down and then goes far to the right. These can be generalized and actually plotted on a log scale. So the difference between the previous graph and this one is really the y-axis. Age is still the same here on the x-axis, but the y-axis here we have number of survivors, and this is a log plot. Whereas on this page, if we go back one, if we go to this one, this is percent survivorship, right? This isn't raw numbers of individuals, okay? So that's an important difference to note. So what I want you to think about in this section is you're going to be learning about each of these different shapes of curves and which types of populations tend to show which types of survivorship curves. There's survivorship 1, 2, and 3. So you need to know what those 3 curves are and examples of organisms that have each one. At the end of the section here, let me turn my page to, they are going to rock your socks, okay? So here they are going to say, okay, we just talked about these curves as constant for a particular species, but that's not necessarily the case. They're going to explain to you that the curves can vary for an organism, and so I want you to pay attention here to what types of conditions and what types of individuals may have different types of survivorship curves. A really, really cool concept. Okay, now we're going to get into another new concept for this section about taking life table data and making it into another type of graph. And here's an example of this graph down here. This is an age structure graph. So first, we're going to turn n of x from your life table into a proportion, and then we're going to plot it for each age class and separate it out for each sex, right? Okay, so here in the smallest age class, right, on the left for males, we're showing the number of individuals. This is in millions for the smallest age class. Number of individuals moving up in age class and up and up and up until you get to the oldest ages up here. So this is really showing you the proportion of individuals in each age class in a really nice visible way. What they've done too for you is they've highlighted the reproductive individuals here in green. That's really helpful since this tells you how much of the population is reproducing at any given time. So I want you to examine this figure in great detail. Mark it up. Put down the percent of individuals that are of reproductive age, the percent that are younger in these younger age classes that will be moving up into that reproductive age. And then I want you to look at the projected population size over time and compare these two populations. You find this is really fascinating. In this type of pyramid structure, this is important to be familiar with. Okay, we're going to move on to the next section. This is our last section. Okay, in this section, you see we have another series of tables, and I'm of course going to focus on those. This is a life table for a hypothetical organism. And now actually I'm going to ask you to look at this and then go back and look at those other life tables we've already looked at. I want you to pay attention to the first and the last rows here. Okay, first row up here, which it won't let me highlight, but whatever. Okay, first row here, last row at the bottom down here. Okay, so if you go back, I want you to note which of these numbers is the same in every single life table. So starting with life table 1, right, we're looking here, we have two values, 1 and 0. Coming back here, looking at these values here, which of these values for these different columns are the same in every single life table that they show you, okay? That's going to be important because that's going to help you when you're making your own life tables. Okay. Now you're going to use these life tables to predict the future, which is something I really love about life tables. I'm actually going to point out a little bit of notation here as well. There's a new subscript. Let's see if we can find it here. Okay, we've got little n, we've got a subscript with a number in it, 0, 1, and 2. That subscript is important. That is referring to, so n is referring to your population size, your number of individuals, but it's not your whole population size. This is just the number of individuals in that age class. So n0 is the number of individuals in this 0 age class. And little n subscript 1, that's going to be the number of individuals in this age class, and so on, okay? If you have a capital N, right over here, they're going to start talking about capital N. Capital N is your whole population size. Add up all these little n's and you will get your capital N. Okay, just need to know what these variables mean and how to refer to them. Okay, so Table 10.3 and Table 10.4 are connected. You can see that the age classes are the same here, but what they're giving you now is the number of individuals in each age class. You see that's not represented up here. They've told you that in the text, and then they filled it in here. So age class 0, you have 20 individuals, and then they're going to have you use the information from the first table to calculate your actual population, right? So if you have 20 individuals and their survivorship, their survival rate is 0.3, you multiply that and you get 6 individuals that survive into the next time step, okay? Same for if you take the individuals of class 1, multiply them by their survival rate, you're going to get 24 individuals, and so on. Everybody from this older age class dies, and so you get 0. And then you're going to use your, right, so we were just using survival rate here to make these calculations. Then you're going to use fecundity because you're going to want to add up how many of the offspring are reproducing then, right? How many of your survivors are reproducing, and then you're going to add in the number of newborns because you have 30 individuals that can reproduce, and how many offspring do they have? You get 108 new babies in this next time step. So here we have a new population of 138, whereas we previously had a population of 100. And so the exciting point now is that you have a capital N, right, total population size here, and then a capital N of time, next time step, t plus 1, okay? So if you use that, they're going to give you a formula that you can use right here, lambda, to look at population growth. So if you take 138 and you divide it by 100, what are you going to get? You're going to get the rate of population growth or decline. And that's a really powerful thing to be able to look at over time. And they've, of course, plotted that for this hypothetical population. Here's your capital N growth rate over time in orange, and then your growth rate for each of those age classes, right? So how many individuals in each age class is plotted. Your youngest age class in blue, the next age class in turquoise, and then sort of reddish here is your oldest age class, okay? And then they've just plotted your growth rate. So this is your lambda over time. It varies for a while, and then it sort of gets to a growth rate of 1.32. And we'll talk a little bit about in class what lambda is like and other ways of measuring population growth. So if you spend some time reading this and answering these questions, I think you'll be ready for lecture. I look forward to seeing you.